Okay, let's just make sure this is all working. Looks good. Looks great. Okay, so this is Mr. Moon's stream. We are out of school today for a heat day, so I want to make sure that the stats classes have the chance to see the slides presented in, I think, an easier format than just giving you the PowerPoints. I will post the PowerPoints today, but I also just want you to have a video of me kind of walking through everything so that you can see sort of how I would talk through these things, because of course I will always add a little bit to what's on the slides. So today we're going to be looking at first 2.1b in this first part of the stream, which is about transforming data, and then a little later on this morning, probably about 9 o'clock, possibly a little earlier depending on when we finish this one, we'll start talking about the normal distribution, which is the 2.2a material. So with transforming data, we want to talk about converting original observations from whatever they originally were, the original units of measurements, to another scale. So transformations can affect the shape, center, and spread of a distribution. Some common times where you see transformation of data are, first of all, any time where you're converting from unit to unit. For example, if you're converting from inches to centimeters, you necessarily need to do some kind of a transformation. On the flip side, if you were doing something like curving a test, that would be a different kind of transformation, because you'd be adding either a flat point value to everybody's test score, or you'd be multiplying all the test scores by some kind of factor. And we're going to look at how both of those affect the shape, the center, and the spread of a distribution. So the first one we're going to look at is adding or subtracting a constant. So this would be the case where you take all your maybe test scores and you just add 5 points to them. As you might expect, adding the same number a, which could be either positive, 0, or negative to each observation, is going to add a to measures of center and location. So these would be things like the mean, the median, the quartile values, and the percentile values. But it would not change the shape of the distribution or the measures of spread. I'm going to show you a visual for this, and it may help you understand. So you'll notice that there's error m down here and then guess m. And what we've done with guess m is that we've just shifted error m up by, I'm going to estimate, about 10 to 15, whatever the units are there. And you notice that this shifts up kind of all the positions of the points, right? So the minimum point shifts up. The mean seems like it probably has shifted up by that flat amount. All those points have each shifted up by the same amount. However, the shape of the distribution is exactly the same, and it's just as spread out. You could imagine taking the new distribution and sort of moving it over and putting it exactly back on the original. The only thing that has changed is that it's moved to the right on the bottom distribution. These are the summary statistics, and again, you're going to see if I can get a laser pointer on here. Not sure I can. So, let's see. No. But I can highlight with the mouse. So you guys will notice that the min has increased, or sorry, the min has, looks like, decreased here from guess to error. Q1 changes, median changes, Q3 changes, maximum changes. The IQR stays the same. The range stays the same. The standard deviation stays the same. The mean does change. So those measures of center definitely change. The measures of spread definitely do not change when we're just adding or subtracting. Let's look at our next example. And this is going to be multiplying or dividing by a constant b. Again, this number could be positive, negative, or 0, with the exception that you can't divide by 0, so try not to divide by a b that is 0. What's going to happen is that it will multiply or divide the measures of center and location by b. So that's true just as it was last time. Those measures of center and location are going to change. This time, though, we also multiply or divide measures of center by, and this is kind of important, the absolute value of b. So if we multiply all the values in a data set by -5, then those measures of spread increase by a factor of 5, not -5. Remember that you're never going to want to have a negative standard deviation, so this kind of makes sense. However, it does not change the shape of the distribution. This is kind of a weird point, and I'm going to show you what I mean by that. We see down here at the bottom that error m has this tight, it's not very spread out, the center's around, I don't know, maybe 0. The mean's probably a little higher than that because of this strong right skew. And it's not very spread out at all. Now when we look at this error ft on the bottom, you notice that it is more spread out, right? The center's probably a little above 0 now. I think that's a little more clear. That right skew is very, very prominent, but the shape is really the same. It's just more spread out. Notice that that graph still has a strong right skew. There's that second peak that's almost as tall as the top one in about the same position. All that has changed is that it's more spread out because we've multiplied the measure of spread by absolute value of b. And again, here are the summary statistics, and what I really want you to notice here is that almost everything changes. Actually, the only thing that stays the same in this case is sample size. And of course, if we had like the kurtosis of this, a measure of the skew, we would see that I think would stay the same in this case as well. That's not something we cover in this course, but if you had some kind of a measure of the skew, we would see that staying relatively the same because the shape of the distribution would remain unchanged. Okay, so those are our two types of transformations for data. And now we're going to talk briefly about density curves. So here's some stuff we talked about in Chapter 1 with a sort of toolkit for graphical and numerical tools for describing distributions. So the first thing we want to do is always plot our data. So you should know by now how to make a couple kinds of graphs, whether those are dot plots, stem plots, histograms. We talked about ogives last time. Stem plots I may have mentioned. Also box plots are going to be very important. Generally the next step is to look for the overall pattern in the data. So things like shape, center, outliers, and spread. Remember your socks, right? The third, you want to calculate a numerical summary to briefly describe center and spread. Generally with this, you want to go one of two ways. You can either go mean standard deviation, or you can go for something like the 5-number summary with maybe median, IQR, or if you want to be very detailed, just go min, Q1, median, Q3, maximum. Those are easily calculable on the Inspire. I'm not going to show that in today's video, but if you're looking for how to do that on the Inspire, I would recommend you look on YouTube for videos showing you how to do one variable statistics on the Inspire or the 84, and also how to do a histogram on both of those devices. Those will be incredibly useful all year for almost every data set we ever get. But we're now going to add a fourth step to this. And this fourth step is that sometimes the overall pattern of a large number of observations is so regular that we can actually describe it not even by using that broken up boxy histogram, but we can actually describe it by a smooth curve. So let's talk about density curves. A density curve is a curve that's always on or above the horizontal axis, and it has area exactly 1 underneath it. If you've ever heard the idea that all the probabilities of a possible situation add up to 1, then you will sort of understand why the area under the density curve has to be exactly 1. So a density curve really is describing the overall pattern of a distribution. It's much like the histogram in that it shows kind of all the possible values in a distribution and how likely each value is. The area under the curve and above any interval of values on the horizontal axis is the proportion of all observations that fall in that interval. So for example, if we were flipping a coin 10 times and wanted to know how many heads we were going to get, if we had a density curve that showed all the various probabilities, the area between 2 and 3 would tell us how likely it is that we're going to get a number either between, well, it's discrete, so this is a weird example, but a number that fell either at 2 or at 3. So let's take a look at an example. The overall pattern of this histogram of the scores of all 947 7th grade students in Gary, Indiana on the vocab part of the Iowa Test of Basic Skills can be described by a smooth curve, and you'll notice that highlighted in red, drawn through the tops of the bars as close as we can. So notice this is a pretty good density curve. We're going to get a nice bell curve shape because we have 947 7th graders, which is plenty. That's a pretty big sample. So that's really what we were looking for, and remember that this density curve, because it's a density curve, must have area 1 beneath it by definition. I'll pause here for a moment. You can check out this Foxtrot comic. Please note that I will not be doing my curves based on student suggestions. Sorry about that. Okay, and we'll move on. So our measures of center and spread apply to density curves as well as to actual sets of observations. What do I mean by that? Let's talk about the median and the mean of a density curve. So the median of a density curve is going to be the equal areas point. So this is the point where the area on the right is equal to the area on the left. The mean, on the other hand, is actually the balance point. So if we built this curve out of solid material, the mean is the point where we theoretically could balance it, where it would not topple over in either direction. So there would be the same weight on each side. Now that's different than the equal areas point, because if the density curve has a skew, the mean will be closer to that end. If you've ever sat on different parts of a seesaw, you know why this works. Because points that are further out are going to, quote, sort of weigh more. They're going to have more leverage, and therefore the mean is going to have to shift out to make that balance out. This is a concept that we can talk about a lot more as the course goes on, but right now I want you to remember that the mean is the balance point, and remember that the mean is still going to shift towards the direction of the skew, towards the tail, okay? The median and the mean, you guys probably already can tell this, they're going to be the same for a symmetric density curve. They both lie at the center of the curve. The mean of a skewed curve, on the other hand, like I just said, is pulled away from the median in the direction of the long tail. I reviewed this yesterday with the other class. I'm going to just tell you guys again so that you remember this key word. Please remember that the median is resistant to skew. So it's not going to be pulled in the direction of the skew because it's only looking for the middle point and not the balance point. The mean, on the other hand, is not resistant to skew, so it will be pulled by that tail. here's a picture just illustrating that, and you'll also notice that whoever has created this graphic has done a really nice job and made the mean look like a balance point that would sort of not make this thing tip over, whereas the median is the equal areas point. So we should see equal area on the left and the right of that median line. And of course, notice that the mean is getting pulled in the direction of the tail in B. Okay, quit the graphic. So what we want to do is walk through the following questions, and we're going to try to answer each of these. So first of all, explain why this is a legitimate density curve. Well, it's above the horizontal axis, and the total area under the curve is 1. About what proportion of observations lie between 7 and 8? Well, I'm looking on the graph. I have this zone highlighted between 7 and 8. It says that the area is 0.12, which means that the proportion of observations is going to be 0.12, or 12 out of 100. That would be 3 out of 25, or 12%. Any of those would be really okay answers. Mark the approximate location of the median. Remember that you want to do kind of the equal areas point. I'm really hoping my mouse is showing up. But you want to pick something that's very centered in the data. Mark the approximate location of the mean. If you can't see my mouse, which does happen sometimes, the mean is going to be a little bit, in this case, to the left of the median because it's getting pulled by that left tail. Explain why the mean and median have the relationship that they do in this case. I would say the mean is to the left of the median because this graph, this density curve, I suppose, has a left skew, and the mean is not resistant to that skew, so it is going to be pulled in the direction of the tail, whereas the median is resistant to skew, so it will maintain kind of that equal areas point more in the center of the data, more under that big hump. Okay, so I'm actually going to stop here. In this section, we talked about percentiles and z-scores. We talked about the ogives. We talked about transforming data, and we talked about density curves. Next up, I'm actually whipped through this one, so I'm going to take a brief pause, but then we'll start the next one. Next up, we're going to talk about the normal distribution, which is going to be one of the most important things we talk about all year in stats. So please make sure that you tune in if you're in section 01. If you're in section 02, you can of course still watch this video. And obviously both sections, if you're not here for the live broadcast, that's totally fine. I am going to post these videos right afterwards. Hope you all are enjoying your heat day. Please stay cool. Please drink some water. For now, this is Mr. Moon signing off, and I will see you all in school tomorrow.